up first. On page 415, you know that energy is the ability to do work. Force, work is the force to move an object over a distance. Calorie, the amount of heat to raise 1 gram of water, 1 degree Celsius. Specific heat capacity, amount of heat to raise 1 gram of a substance, 1 degree Celsius. Latent heat is the heat absorbed or released during a phase change. Exothermic reaction releases energy. Endothermic reaction absorbs energy. Kinetic energy is energy in motion. Potential energy is stored energy. Okay, blank is the study of heat that is absorbed or released by chemical processes. Thermochemistry, very good. Number 3, what is wrong with the following statement? If there is no temperature change, there is no heat change. It could be a phase change, don't forget that. Number 4, which of the following units would be acceptable for measuring heat? Calories and joules, right. Number 5, a Hostess Twinkie contains 270 real calories, food calories, not chemistry calories. How many grams of water would you warm 1 degree Celsius with that energy? Well, remember, 270 calories, as in food calories, is 270,000 chemistry calories. So how many grams of water would you need to raise it 1 degree Celsius? 270,000 grams. Wow, okay. There goes the Twinkies. Okay, number 6. Let's see. Glass has a specific heat of 0.840 joules per grams degrees Celsius. Solid magnesium is 1.020. And solid silver is 0.24, all of that. If I add equal amounts of heat to equal masses of these substances at the same initial temperature, so we're trying to do, starting them all at the same place, which gets warmest? So which one is the easiest to heat up? Silver, because it's got the lowest specific heat capacity, so it's the easiest to warm up. Which one stays the coolest? Magnesium, because magnesium has the highest heat capacity, and therefore you have to add more energy to heat it up. You have to take away more energy to cool it off. Very good. Number 7, which of the following is a unit for specific heat capacity? So which one would that be? Good. Joules per grams degrees Celsius. Which one would we use for heat capacity? That's joules per degree Celsius. That's the big C that we used for the calorimeter. So just remember that heat capacity is M times little c. So that's just going to give you joules divided by degrees Celsius. Number 8, a 2.5 kilogram sample of copper at 24.1 degrees Celsius experiences a change in temperature to 19.7 degrees Celsius. How much energy is involved? Did the copper gain or lose energy? Okay, here we're going to be using our Q equals MC delta T. And we are given our mass at 2.5 kilograms, but we know that we're going to need this in grams because this is given to us in joules, grams, degrees Celsius. So I'm going to go ahead and convert that to grams. There we go. So there's my mass. And then C is given to us for copper, so we're going to plug that in. Grams, degrees Celsius. That's why we had to go to grams there. And then we need the delta T. Okay, and we're going to need to find delta T. That's usually going to be the case. Delta T, remember, is the final minus the initial. And so here, experiences a change in temperature too. Okay, so the final is 19.7 degrees Celsius minus the initial we're given as 24.1 degrees Celsius. And so that's going to give us negative 4.4 degrees Celsius. So I'm going to put that in here, negative 4.4 degrees Celsius. It goes to the ones place. Remember, when you add or subtract, you have to use the least precise. So even though these have 3 significant figures, that is your answer. And now those 2 significant figures are going to limit everything else, although this is in 2 significant figures also. So when you do this in your calculator, let's do it. 4.4 negative times 0.386 times 2.5 EE3. What comes out in my calculator is negative 4246 joules, but I can't keep that, can I? Because this limits me to 2 significant figures. So this is going to have to be negative 4,200 joules, because that 4 doesn't round up. And you only look here. You don't look here and go, oh, well, that rounds that up, so that rounds that up. No, you only look one past, and that's a 4. So you're going to give that as 4,200 joules. Now, with that in mind, with the 4,200 joules in mind, it says how much energy is involved, 4,200 joules. Did the copper gain or lose energy? Well, that negative sign tells you that the copper lost energy, and that would answer that. Number 9, 500 grams of water in its liquid phase loses 5892 joules of heat. If it started at a temperature of 25 degrees, what is its final temperature? Okay, so we're still using this, but in this case, we are told Q, and we're told that we lost that much temperature, so we're going to put in 5892 joules equals, we are told that we have 500 grams, so we're already in grams. That's nice. Water's C is 4.184 joules, grams, degrees Celsius. There. And we are looking for something within the change in temperature because we're looking for its final temperature. The initial temperature is given to us as 25 degrees Celsius in 3 significant figures. There we go. So that is your setup. And if you have that much on your test, I'm going to give you some credit because then it can be algebra issues. So if you go ahead and you, let's see, divide by that, and so ultimately what you're going to end up with is, I'm going to go ahead and do this. If you divide by those 2 numbers, you end up with this. And then the joules would cancel, the grams would cancel, and you'd be left with degrees Celsius equals the final temperature minus 25.0 degrees Celsius. So then you would flip this over there, and that gives you, yeah, that's the right number of significant figures, but you have to end here. So the final temperature is going to end up being 22.2 degrees Celsius. Because look at this, if you went ahead and added that to that, so you have negative 2.816, negative. And then you add to that, because you're going to add to both sides, 25 degrees. What comes out in your calculator is I'm going to show you 22.184, but this has to be to the ones place, excuse me, to the tenths place, because you have to go with the least precise. So you're going to round that up, and that's where you got that answer. So if you just fill this in, you can see what you're solving for, and then you've got to do your algebra carefully. You had 4 significant figures on each of these. That's why this had 4 significant figures, but when you got to this part, you're adding or subtracting, and therefore you have to go by the least precise. So it's a bit tricky on the significant figures. You got to watch yourself there. Number 10, 175 grams of an unknown metal gain 5.6 kilojoules of heat. The metal's temperature rise from the metal's temperature rises from 24.3 degrees Celsius to 110.5 degrees Celsius. What is the specific heat capacity of the metal in joules per grams degrees Celsius? Okay, so here we are actually looking for C. So I'm going to go ahead and solve for C, and I'm going to go Q over M delta T. That's what we're looking for. Let's start plugging in. So we are told here that it loses 5.6 kilojoules. So we're going to go times 3, and that would be joules, because we know we want this in joules, grams, degrees Celsius. So that's why I went ahead and converted that. And then we are told the mass is 175 grams. So there's M. I just plugged that in. I plugged that in. Now we have to find delta T. And delta T, we're told that the metal's temperature rises from, which is the initial temperature, to 110.5. There we go. Okay, so that's going to give us 86.6 degrees Celsius. So I'm going to put that in here, 86.6 degrees Celsius. Now, this has two significant figures, so that's going to limit my answer. So when you do this, it's going to give you 0. In two significant figures, 37, and then you have joules per grams degrees Celsius. They're right there. So once again, your units will tell you if your numbers are in the right places. And then watch your significant figures, and you just literally write out your equation and then start plugging things in. And if you're missing something, go find it, which is what we did, and then plug it in. Number 11, why does a calorimeter need to be insulated? Who wants to tell me? Why does a calorimeter need to be insulated? Right, so you don't get a heat exchange from the environment. No escape, no absorption, right? It's a closed system. Number 12, why does a calorimeter need to be stirred so that the liquid allows the heat to be distributed? 13, if a calorimeter experiment has two things, in a calorimeter experiment, what two things start off at the same temperature? Liquid in the calorimeter. And what ends at the same temperature? Everything. Number 14. A calorimeter experiment is performed on 112.1 gram sample of metal. It is heated to a temperature of 175 degrees Celsius, put in a calorimeter that contains 250 grams of water. If the water's temperature rises from 27.1 to 31.7, what is the specific heat capacity of the metal? Ignore the calorimeter in the calculation. Yay! Okay, so I always like when we can ignore somebody. So we know that the energy that the object loses, which is QC delta T, silly. We know that the energy that the object loses is absorbed by the liquid, don't we? So that's what it loses, that's what is absorbed. And we know that that equals mc delta T of the object equals mc delta T of the liquid. Okay, so far so good. And we're trying to find what is the specific heat capacity of the metal. This is what we're trying to find is C, because this is the object, so that's the metal. We're trying to find C. Okay, so let's start plugging things in. The sample of metal, its mass is 112.1 grams. We're trying to find C. And its temperature, it is heated to a temperature of 175 degrees. Okay, so we're going to find the change in temperature of the object, which is the metal. It was heated to 175 degrees, so that is its initial temperature. Put in a calorimeter. And the final temperature in the calorimeter is 31.7 degrees Celsius. And so that's going to give you your change in temperature. There it is. So this is negative 143.3 degrees Celsius. So I'm going to put that here. Negative 143.3 degrees Celsius. So far, so good. We've got this. Now, everybody saw that. And just in case you're wondering, it said it heated the metal to this, and then it said that the water temperature went from 27.1 degrees to 31.7 degrees, so that means that's the final temperature of everything. So that's where I got that. Okay, and remember it's final minus the initial. That gave us the negative. Getting rid of this, so I have room. Okay, now we're over here. We have the mass of the water is given to us at 250 grams. We have memorized that the water is 4.184 joules per grams degrees Celsius, just from doing so many problems. And we know that the change in temperature of the water went from 27.1 degrees Celsius to the final temperature of 31.7 degrees Celsius. And so that gives me a change in water temperature of 31.7 minus 27.1. 4.6 degrees Celsius. Yes. And so I'm going to come in here and I'm going to put 4.6 degrees Celsius. Okay, now the Celsius will cancel, the grams will cancel, and I'll be left with joules, so that's a good thing. Okay. But then we're going to swing those two over here, aren't we? Let me just do this. We're going to actually swing, these are going to make positive. We're going to swing that over here. So I'm just going to show you. I'm going to divide both sides by that. The negative and the negative will make that a positive. So I'm going to put the 112.1 grams here. And I'm going to put the 143.3 degrees Celsius here. Okay, now the Celsius will leave, the grams will leave, and we'll be left with joules over grams degrees Celsius, which is what we need. These are no longer over here, so we're going to find the C of the object, which is the metal. We have two significant figures, which is going to limit us. All right, if you multiply across here, and this is limited by two significant figures, you get 4,811.6. So I'm just going to go 4,800. And then that'll cancel, we'll be left with joules divided by, and then this, I have four significant figures, 1606, and this is grams degrees Celsius, but these two significant figures are going to limit this. When you do this in your calculator, you're going to end up with something like this. But remember, you have to have two significant figures in your answer. So you're going to roll that to two significant figures. So your answer would be 0.3 joules grams degrees Celsius. Now I'm going to tell you right now, I've edited this a lot. And with all these numbers, it's really hard to get the same number twice sometimes. Maybe you're better with your calculator than I am. So make sure you do it a couple of times and get the same number a couple of times. Otherwise, don't trust your numbers. Okay, because I got different numbers a couple of times. My decimal place was off. So be careful with that, okay? Number 15, a 145 gram sample of tin is heated to 150 degrees, dropped in a calorimeter, contains an unknown mass of water. If the water starts out at that temperature, ends up at that temperature, what mass of water was in the calorimeter? Ignore the calorimeter for your calculations. So we are back to negative Q of the object equals the Q of the liquid, which in this case is our water. And remember, that means that it's negative MC delta T of the object equals MC delta T of the liquid, which in this case is the water. Okay, remember that's the energy that's lost is gained by the liquid. So on 15, we have 10 as our sample. So we're going to go negative, and we have 145.1 grams. Whoops, it's not a very good parenthesis. And then we're given C of tin as 0.210 joules per grams degrees Celsius. And then the temperature change, we know that the tin is heated to 150 degrees Celsius. And we know that the water ends up at 30 degrees Celsius. So that is going to give us negative 120 degrees Celsius temperature change, isn't it? And so I'm going to put that in here, negative 120 degrees Celsius. Okay, equals, now we're looking for the mass of the water. That's actually what we're looking for. So I'm going to leave that. The C of the water is 4.184 joules grams degrees Celsius. And the change in temperature of the water, I'm going to go ahead and do that here. The change in temperature of the water, we're told that it started at 22.6 degrees Celsius and it ended at 30 degrees Celsius. So that's going to give us a temperature change of 7.4 degrees Celsius. So I'm going to put that here, 7.4 degrees Celsius. Okay, now we can go ahead and, let's see, we'll do 4.184 times 7.4. So this, it comes out as 30.96, blah, blah, blah. It's got to be in two significant figures because of this. So I'm going to make that 31. So I'm going to divide this side by 31. This will cancel. We'll be left with joules per gram. Okay. And so then when we do this, we see that we're limited by two significant figures. There we go. The negatives will make it a positive. And so the mass of the water ends up being, in two significant figures, 120 grams. So it's a matter of plugging in, watching your significant figures, and working very carefully on your calculator. Number 16. An object has a heat capacity of 16.7. How much heat must it absorb to increase its temperature by 5 degrees Celsius? So this one, we're doing heat capacity. And so that would be Q equals C delta T. And we are given its heat capacity as 16.7 joules per degree Celsius. And it says how much heat must it absorb to increase its temperature by 5 degrees Celsius. So that is the change in temperature. So the change in temperature is 5 degrees Celsius in two significant figures. And so that's going to give us 84 joules, two significant figures. 84 joules. Number 17. A metal object has a mass of 315 grams, is heated to 317 degrees Celsius and dropped into a calorimeter, has a heat capacity of 1,300 joules per degree Celsius. The calorimeter contains 500 grams of water at an initial temperature of 25.6 degrees Celsius. If the water's temperature rises to 31.5 degrees Celsius by the end of this experiment, what is the specific heat capacity of the metal? Okay, so we are doing this. And so the metal mass is 315.0 grams. It's heated to, it's going to be my change in temperature, 317 degrees Celsius. It's dropped in a calorimeter, has a heat capacity of that. Oh, this time we have to take into the account the calorimeter. That would be, okay. All right, so back to this. And the final temperature is 31.5 degrees Celsius. So that's going to give us minus negative 285.5 degrees Celsius. So, and do we have the, oh, we're looking for the specific heat of the metal. Wow, there you go. That's why I couldn't find it. Negative 285.5 degrees Celsius. There we go. Equals. All right. So far, so good. Now we're over to here. Mass of the water. The mass of the water, 500 grams. Water is 4.184 joules, grams, degrees Celsius. Change in temperature of the water. It says that the water had an initial temperature of 25.6 degrees Celsius and a final temperature of 31.5 degrees Celsius. So final minus the initial. That would give us a 5.9 degrees Celsius change in temperature for the water, 5.9 degrees Celsius. There's our change in temperature for the water. And we are told that the heat capacity of the calorimeter, so we're just going to add that over here, is 1,300 joules per degree Celsius. There we go. So that actually takes care of that. Okay, because it takes into account the grams. So, if you do all that, this ends up giving you what I've got here is in two significant figures because of that. Let's see, that'll leave. We have joules plus the 1,300. Oh, shame on me. We still have to multiply this by the change in temperature, 5.9 degrees Celsius. Some of you caught that and you were waiting for me to do that, weren't you? So you still, it takes into account the mass, but it didn't do the energy change in temperature. And so I got the change in temperature there. So now this is going to give us over here in two significant figures, 7,700 joules. Now, when you add these two up, I'm going to put it underneath it so you can see it. Okay. 0.00791. This is the precision, the least precise right here. So that's what we have to have our significant figures to. So this answer is actually going to be 2, I want to make sure you can see that, 2, 0, this being the significant figure, 0, 0, 0. So if this is the significant figure, then we have to put this as 2.0 times 10 to the 4th joules, don't we? 1, 2, 3, 4. 2.0 times 10 to the 4th joules. That's how that would have to be handled because of the significant figures. And then if you came over, okay, so if we have that and we divide it by these two numbers, okay, you need an answer in two significant figures. So when you have this number and you divide it by these two numbers so that you get C, C ends up being 0.22 joules, grams, degrees Celsius. Ho-ho. A lot of places to mess up there, huh? Make sure you show all your work. Give yourself a lot of time to take this test. And make sure that you do all your numbers a few times. And if your units don't line up, go back and figure out what you were missing, like right there. I was missing something, wasn't I? So let the units help you. 18. An iron object has a mass of 275 grams, is heated to 165 degrees Celsius, is dropped into a calorimeter with a heat capacity of that. The calorimeter contains 500 grams of an unknown liquid at a temperature of that. If the liquid's temperature rises to that by the end of the experiment, what is the specific heat capacity of the liquid? So we're looking for C of the liquid. And here, whoa, I erased everything. We have negative Q of the object equals the Q of the liquid plus the Q of the calorimeter. And so I'm going to go ahead and write it out because it just makes it easier. Mass C delta T, that's the object, equals mass C delta T of the liquid plus the mass C delta T of the calorimeter. Okay, and here we are looking for the specific heat of the liquid. So this is what we're looking for in this particular instance. Let's start plugging in. We have a mass of iron as 275.0 grams of iron. The C is given to us as 0.444 joules per grams degrees Celsius. It is heated, so we're going to find delta T now. It is heated to 165.0 degrees Celsius. The final temperature is 31.5 degrees Celsius. And so, whoops, I'm so sorry. I'm looking at the experiment right above it. And its final temperature is 51.5 degrees Celsius. There we go, by the end of the experiment. Okay, good. All right, so that gives us a negative 113.5 degrees Celsius change. So I'm going to put that in here, negative 113.5 degrees Celsius. There we go. That's this. Equals M, whoops. The mass of the liquid is given to us 500 grams. We're trying to find C. And the change in temperature, that's going to be the final temperature for everything, isn't it? The initial temperature of the liquid was 45.3 degrees Celsius. And so that's going to give us 6.2 degrees Celsius is the temperature change. So 6.2 degrees Celsius. Okay, now we've got that. Plus, the heat capacity is given to us with the M and the C into account. And so the heat capacity is 1,300 joules per degree Celsius, and here we have a temperature change of 6.2 degrees Celsius, because it'll be the same as the liquid. Now, if you do all that and you are solving for C, and you have to have two significant figures, there's two there, there's two in several places, you will end up with an answer of C equals 1.9 joules grams degrees Celsius. And I'm going to let you play with all the arithmetic just for speed. That's how it lays out. 19. How much energy is required to vaporize 4.51 kilograms of ethanol? Okay, so with this one, we are dealing with the latent heat. So we're going to ditch this because we're not dealing with a calorimeter. And the equation we're going to be using is Q, this is the energy now that we're looking for, is the mass times the latent heat. And so, let's see, the mass we're given is in kilograms, so we're going to have to convert that to grams. 4.51 times 10 to the third grams. And the latent heat that we're given How much energy is required to vaporize? Okay, so first we are going to use the one that is the LV because we're looking for vaporization. And so we're going to use 838 joules per gram. And notice that will end up giving us joules. And in three significant figures, it gives us 3.78 times 10 to the 6th joules. So here we just need to know this, and because we're vaporizing it, we chose the LV to plug in here. Number 20. A 136 gram ice cube at negative 15 degrees Celsius is heated until it is liquid with a temperature of 50 degrees Celsius. How much energy did it absorb? Okay, so first we have to take our ice cube and melt it and get to 0. And then we take it up to 50 degrees, so it's going to stay liquid. So the first thing we do is, excuse me, we have Q equals MC delta T, and this is to get to the melting point. Well, what's the melting point of water? It's 0 degrees Celsius, correct? And so we're going to go here, let's see, the mass, 136.0 grams, 4.184 joules, grams, degrees Celsius. And here we are just trying to get it to 0. And let's see, the ice cube is at, its initial temperature is negative 15 degrees Celsius, and we're trying to just get it to 0 degrees Celsius. And so it's going to be minus the negative, and so it's going to be 15 degrees Celsius. Okay, so we have 3 significant figures there, and so our answer has to be in 3 significant figures, and you'll be left with joules, so that's going to give us 4,270 joules. Okay, that first step just gets us to 0 degrees, which is the melting point. Then we actually have to go through the energy to melt the water. So that would be found with Q equals M L, and that is LF. Okay, and so here we still have 136 grams, but here the LF of water is given to us as 334 joules per gram. 3 significant figures our answer has to have, and so it's going to be 45,400 joules. The grams will cancel. Now we have gotten our water to the melting point. Now we have the energy that it takes to transition it from ice to liquid waters, but still at 0 degrees. So now we have to figure out the energy, getting it to 50 degrees. Yes. Okay, so we still have 136. We still have 4.184. Only now our change in temperature is going to be, the initial temperature is 0 degrees, and we're taking it to 50 degrees Celsius, and this is minus. And so our change in temperature is 50 degrees Celsius. Some of you are looking at that going, you didn't have to do that step. We could see that. It's okay. Joules. Okay, and now that we've got all that, I'm going to erase this because I want to show you something. Okay, I'm going to keep those answers though. Okay, now let's look at the significant figures. First one is 4270 joules. The second one is 45,400 joules. The last one is 28,500 joules. Just make sure I wrote all these correctly. Oh, that's 49. That one. Nope. It's 48. Okay. Okay, so far so good. So when we add this up, we end up getting 0, 7, 6, 11, carry the 1, 10, 18, carry the 1, 7, 78, 70, 170. But you can't leave it like that because this is the least precise to the hundreds place. So we have to have an answer to the hundreds place. And because this next digit is actually going to round that up, we are going to answer with 78,200 joules. And that would be how much energy is required to do what it asked, to take the ice cube from negative 15 degrees and take it up to 50 degrees Celsius. So remember, we had to go through 3 stages. We had to go from negative 15 degrees to 0. That was this. Then we did the heat that it would take to take it from an ice cube to liquid water, and that would be still at 0 degrees. And then we took it from 0 degrees to 50 degrees. And so that's this. And then you watched your significant figures here. Let's go down to number 21. 21, a chemical reaction occurs in a beaker and the beaker gets cold. Is it endothermic or exothermic? Endothermic. Number 22, when it comes to chemicals, where's the potential energy stored? It's in the bonds. Number 23, is combustion exothermic or endothermic? Exothermic. Is the heat you feel from the fire kinetic or potential? Kinetic. Let's do the problem on page 406, please. Okay. I personally think these are the most confusing, aren't they? Okay, so let's just do this one. It says a 300-gram sample of ice at 0 degrees is converted into water vapor at 100 degrees. Oh, this one's not hard at all, is it? How much heat is absorbed by the sample? So here we're starting at 0 degrees. Okay, so it starts at 0 degrees. And then we have to go up to the boiling point, which is 100 degrees. And then we have to get through. It did start as ice, didn't it? It did start as ice. Okay. No, but it started at 0 degrees. So we just, yeah, I guess I should draw it that way, shouldn't I? It's ice at 0 degrees. Then it had to get up to 100 degrees, and then it vaporizes. There's our 3 steps, right? If it started below 0, then we'd have another step, wouldn't we? Okay. So we have 1, 2, 3 steps. I'm going to number them. 1, 2, 3 steps. Okay. Here we're just trying to do a phase change. So the phase change is just going to be Q equals mL. Here we're actually going to do Q equals mc delta T. And up there we're going to do Q equals mL. Right? Okay. So we have 300 grams, so we're going to go 300. And then that one is going to be LF, which we've already used several times, 334 joules per grams. This one is 300, 4.184 joules, grams, degrees Celsius. And the change in temperature here is 100 degrees. It's 100 minus 0, so it's 100 degrees. Infinite number of significant figures. And then this one is the 300 grams times LV, which is 2260 joules per grams. Okay, so when you do this, watch your significant figures. This answer is going to have 3 times 334. So the comes out is 100200. But I have to have 3 significant figures, so I'm going to answer that as 100. I have to have 3 significant figures. So I'm going to have to put that in scientific notation, aren't I? times 10 to the 1, 2, 3, 4, 5. Okay? All right, this one has 4 significant figures, 300 times 4.184 times 100. This says 2520, 4 significant figures, 122500 joules. And then this one has 3 significant figures times 2260. This gives me 678,000, 3 significant figures, so that's good. Joules. Now, the tricky part is adding them up. And so what I'm going to do is that first one is 5 significant figures. 5 places. So I'm going to go 1, 2, 3, 4, 5 zeros. And I'm going to put a line under where my significant figures end so I can see what I'm doing. Okay? Second one. 1, 2, 2, 5, 0, 0. Third one, 6, 7, 8, 0, 0, 0. Okay, so you're just going to add those up, and your significant figures have to end here. Okay? How we doing? Not so bad if you do it with the graph, right? Do it with the graph first. Figure out what steps you have to take. Remember, the steps that are phase changes are going to be this equation. The steps that are a change in temperature are going to be this equation. Okay? And you know that LF is where it goes from freezing to liquid, and LV is from the liquid to the vapor.